Hello everyone and welcome to First in Focus. Today with us we have FRC Team 1678, the Citrus Circus from Davis, California. They have a 7-year Einstein streak and are well known in the FIRST community for their creative and effective robot designs. Today's focus is on how to design with manufacturing in mind, how to plan manufacturing resources, how to manage Onshape CAD and drawing releases, managing part numbers, and designing in a 1678 style. Questions will be answered at the end, but feel free to drop any questions you might have in the Q&A box during the presentation. Now, without further ado, I'll hand it off to Citrus.
Thanks, Christine. So we're really excited to share this little insight into our design process. I'm going to kick it off to Nathan, our design lead, to start with some introductions.
How's it going? My name is Nathan McAllister. I'm the design lead on 1678 and also the operator.
Hi everyone, my name is Atara. I'm a design member on Team 1678, and during competition I help other teams.
Hey guys, I'm Zach, and I am a design member, and I am our human player.
And I'm Mike Corsetto. I'm one of the mentors on 1678. I've been mentoring the team since 2008.
All right, so we'll get right into some of our design philosophy just to preface a little bit and start out with like where we come from, how do we approach design in general, I guess. So if you've been around our team at all, you've definitely heard the slogan, steal from the best, invent the rest. So this just goes to show you don't have to come up with everything yourself, right? You have years of experience of your own team and other FRC teams. And from those years of experience, you know what works and what doesn't. So a lot of times it's super easy just to look at past designs and take what works and omit what doesn't. And then next we have keep it simple where possible. So pretty straightforward. You don't want to overcomplicate things where you don't have to. And that also comes from experience and stealing from the best. And then next, constantly iterate. This is a crucial thing for our team. So the reason we are at a high competitive level is because we go through so many iterations of each mechanism. So for example, in 2019, the hatch panel mechanism alone had 7 iterations, I think, before the final one on the competition robot. And then going along with that is drawing the good enough line. So what I mean by that is you don't want to keep things in CAD forever. So the only way you're going to get iterations is by accepting, okay, this is going to be good enough for what we want to do. I'm just going to send it out, see how it works, and then we're going to improve it by there or from there. So you don't want to be stuck in CAD saying, oh, but if I just spent one more day on this, it could be even better. A lot of times, I guess it's a balance, but a lot of times it's good to just get things out there and get them tested and go from there and do it quickly. So kind of building off of that, this was the first iteration of our robot. And it looks nothing like, well, looks a little bit like what we have currently, what you saw in the render on the last slide. But you can see everything is just kind of thrown together. The intake is permanently out. Everything is good together. The polycarb is just super messy. The shooter is made out of laser cut plywood. Like, this is not a competition ready robot, but this is the robot that we did our 10-ball reveal video with. So this is kind of our process in that we just try to get something out, get something to the programmers as soon as possible. I think we had this robot done by the end of week 4 and just started testing and getting our autos working and improving CAD from there, from all the testing and all of it. So yeah, that's just an example.
Wanted to also just mention, you know, a big part of this process is the 3 students on our team that are in this call, you know, have done 90%, if not more, of the CAD on the robot. And so, you know, as students with a lot of years of experience to lean on, but not many years of experience themselves, it's important to build quickly so that they're able to identify mistakes that might get made through the build process. It can be easy to spend weeks and weeks in design and not realize all the things that you don't know. But the best way to find out what you don't know is to make it once and figure out all the ways that it can actually fail. And so this example of this picture that Nathan showed is that methodology in action.
All right, so we're gonna start from the beginning here. So I think that this drawing that is on the right, I think I did this on day 3. And you can see this looks a lot like 973. It's a tall robot. And this robot met all the criteria that we wanted to. We initially decided to go tall, actually, which might come as a little bit of a surprise. But really the limiting factor was the climber. And once we figured out how to get the climber to fit under the trench, we were just going short from there. But pretty much our design process is for the first week or so, we are doing drivetrain and we are doing Crayola CAD and mock-ups for the rest of the mechanisms. And then the goal is always have the drivetrain done super quickly. And then weeks 2 to 4 are spent on mechanism design and iteration. And then we tend to do design reviews about twice a week. And then the reason we're able to iterate so fast is because a lot of our design work is done at home, and most designers are not doing design at the shop. They are doing prototyping and assembly. So if Mike, you want to switch over to the mock-up of, I guess, the week 1 demo assembly.
Sorry, I forgot to refresh all our Onshapes before the call. My bad.
Yeah, that's the same sketch as the picture, and then the parts they do in assembly in that same document.
Yeah. Oh, I guess I could have just gone to that, huh? Here we go.
Yeah.
You can just look at this before I refresh. How about that?
Yeah. So obviously this is a current drivetrain, just because everything kind of broke throughout the 2 months of build season after I put this together. But this is week 1, just kind of extruding very simple parts and seeing how everything is going to fit together. So you can see based on our goals, we decided to prototype a Wheel of Doom. And once we felt confident enough to proceed and felt like we could get it to a place where it's efficient enough to run on a real match, we committed to it. And then that Wheel of Doom, the indexing system that we used kind of warranted this design, because obviously the shooter has to go in the middle of that, and then you have the column pulling the balls up, and then the climber has to go in the back. So that was kind of the thought process behind this whole design. And by mocking that up in the first week, you have a clear path forward, and you can really detail out from there. Oh, looks like we have a stray word down there. Okay, we're good, never mind. So the 1670 design style just generally is a drivetrain constructed of 2x1 tubing. We usually use 16th inch wall on the front and back and 1/8 inch for the sides. And then from there, we mount some frame members depending on what our mock-ups show us, where we want the mechanisms. So in this case, we mounted some frame members to the back because that's where the climber is going to get mounted. And then from there, all the mechanisms just mount to either the drivetrain or the frame members that we put in place. So we actually ended up adding some horizontal ones that aren't shown here. But this is where we start. We just commit to it, don't overthink it, and then we design around what we've committed to. And I guess this kind of on the same lines, we try to have drivetrain design done pretty much immediately. So we've decided what drivetrain we're going to use by day 4 or 5-ish, and design is usually done by the end of day 5. And we do this by just, we have a lot of our old robots laying around. So this year we took one of the 2x1 steel bars, rolled our robots across it, and we're like, okay, this one works best. And we were most impressed with the performance by our 2016 robot. And then we decided just to take out the middle wheel. Yeah, I guess some conventions we tend to put in place are all the main electronics go on the belly pan, and we put them there without really knowing what the rest of the robot is going to look like, just so that we can forget about them, not worry about them, and they usually won't get in the way if they're set in like they are in the render here.
All right, so I'm going to take you guys through the tools that designers on Team 1678 use. I'm sure that if your team uses CAD to design your robots, many of you guys are aware that there are a lot of online resources that can help you calculate things such as center to center distances between gears or belts. On Team 1678, we've actually taken all those calculators and placed them into one large spreadsheet document. We call this tool the design tool. So on this document, we store information for our motor systems here. So for example, on the motor systems tab, we have the output RPMs for each of our motors, how we're tracking it, so perhaps maybe a talent encoder in the Falcons, or maybe even proximity sensors. As for the pneumatics tab, or the pneumatic systems tab, we list down which cylinders we'll be using just so we can calculate how much air we'll use per match and how much air tanks we'll need on the robot. All right, let's move to a motor. So every single motor, which corresponds to its mechanism, every mechanism, or more so, gets its own motor, right? So on its own tab, we keep track of the gears that we use for that gearbox by entering A, what motor we use, B, the gears that we use, and then some other extra information, some extra tidbits such as, let's see, on this one linear mechanism, we'll add the applied load that there'll be on that mechanism. And basically what this does is that with the calculator, we're able to get information such as current draw, stall loads, etc. And then finally, we also have your standard center to center calculator. I believe we stole this straight off of West Coast Products, and it just helps us calculate center to center distances and keep track of what those distances are. So the reason why this tool is, mostly useful is because it A, informs the programmers of what we're doing, and then B, keeps track of everything, and then C, we can also make quick changes, iterations, and all that good stuff, and making sure that everyone else is informed.
Yeah, just to add on to that, like Zatara mentioned, our programmers are utilizing these motor RPM to output RPM ratios in order to effectively calculate, for example, like the exact ratio for the hood really matters because the programmers need to know how many rotations of the motor equals a rotation of the hood so that they can effectively limit the travel of the hood on this year's robot. I think we have a story when the hood was not reaching its max limit, and it's because we didn't use the gear ratio that we had in our calculator on the prototype robot because it was the gears we had in the shop, and so the ratio was a little different, and the programmers were very confused, as were we, until we realized that we didn't use the right gears. So this is meant to be a communication tool between the design program and then other groups on the team. Okay, we'll go back to it. All right, design reviews. So this is the one slide I get to talk about. You heard earlier, and I'm sure you've seen, we use Onshape for our CAD. Our designers are designing mostly from their own homes on their own time. And so I would say probably about 70%, maybe a little bit more, of the actually looking at the CAD reviews that happen are done remotely. And so we're using a combination of either just Slack and screenshots, or I have a slide template, which I'll show in just a little bit. But the way that it works normally is the designers will just ping me on Slack when their subsystem is ready for a design review. Like this could look like a very basic layout design review like Nathan showed at the beginning. It may be a full mechanism where they have a mechanism detailed out and they want to ask, what do we need to change, things like that. And myself or sometimes Nathan will provide feedback. And the important thing about the design review process is that the reviewer, typically the reviewer is someone with more experience and knowledge of the subject matter. So in this case, design. So I've been doing this for a very long time. I've seen a lot of robots. Nathan is the lead design on the team and has a lot of experience as well. So, we're in a good position to give feedback to our other design students on their mechanisms. But it's important to communicate clearly. So I developed this little design review template document that I try to use for each review that I go through with the students. Obviously, sometimes I'm not using this system. I'm just using Slack screenshots or screenshots from my phone because Onshape is really nice and I can view it from my phone. But what I try to do is I try to label each of my feedback items so that students are able to track the thought process behind my feedback. And it can get pretty specific. It can be, sometimes it's just layout specific. So for example, we were copying the 148 Wrangler from 2018 for our 2020 Wrangler, and Zatara was the lead on this design. So initially we just had mocked up the Wrangler to be in the top level of our mock-up robot. You might actually recognize this blue hood from that mock-up image we looked at a couple minutes ago. But there were a couple of issues with the packaging on the Wrangler, so we figured out pretty soon we needed to have the upper and lower jaw be separate from each other. And so you can see here that I'm trying to say, okay, red arrows are where I think we need to have the cylinders that are deploying the green upper jaw. And then, you know, green is the upper jaw, orange is the lower jaw, and then there should be cylinders between the green and the orange to further deploy the lower jaw so that the jaw can be collapsed and then go down in 2 different stages and go from a collapsed upper jaw where it doesn't get in the way of the indexer to a open lower jaw. So I'm using this format and just a couple of minutes in Onshape and taking a couple of screenshots, typing this up, and then I'll send a Slack to Zatara through our design channel and say, hey, Zatara, I have a couple slides, check slides, you know, whatever this is, 5 and 6, and I have some Wrangler feedback for you, right? So this process lets, you know, people with more experience on the team, you know, I really enjoy this feedback process. I don't do the CAD myself personally, but you know, the kids are the ones that are really taking ownership of this. So they're able to take this feedback that I give them and apply that to their designs and further refine their mechanisms. Okay, we're gonna start with our designing for manufacturing. Zatara.
Awesome. So as you guys know, obviously designing FRC robots is limited to what machines you'll be using. So for example, in our shop, our machines, our parts are machined on manual mills, manual lathes, CNC routers, laser cutter, and we also have some 3D printers. So because we only machine on those machines, we have to primarily use what we can attach to those, such as rectangular round tubes. We also use shaft for the lathes. We have aluminum plates that we can use on the router. We also cut out polycarb sheets on the router. And then for the 3D printers, we use PLA and Onyx. So basically the general rules for all of our new designers and also veteran designers is that plates will be used on the CNC router. So CNC features go on plates, not tubes, except for our drivetrain tubes, just because those have to be a bit more exact. And we also make sure, or we emphasize, that our designers have to be able to physically run those machines. So for example, one instance is at the beginning of the season when we train our designers, we actually teach them how to use the machines as well as how to use CAD, just so they're able to know what they can edit, or sorry, what they can design based around that. One big tip I have for you guys is know your machines. For example, make sure you know the end mills that your team uses. Note that one example is that end mills have a radius, so make sure to fillet all of your radius edges inside your CAD model.
All right, so now we're going to kind of talk about just some general part conventions, some just general rules that we go by with designing parts. So for tube, for example, this is actually one of the ways that we can pump out some of our assemblies really quickly, like our drivetrain, for example, without needing to worry about too much about how it's going to interact with everything else, is by using our half-inch hole pattern on tubes. So for example, we'll take these, number 11 size holes, and we put them in a linear pattern that goes half-inch from each of the walls of the tube, and it goes across the entire tube. This gives us this nice standard pattern where we can pretty much just add things onto wherever we want. It's way more flexible for us, and also it tends to save us a lot of weight too. For shafts, we use snap rings at the end of them, generally as just to hold them all in place. We go with 40 thousandths of an inch wide little grooves at the end of the shaft with a little shoulder at the end of it too. And we'll generally make our shafts, the actual hex shoulder in the middle of it will be 10 thousandths of an inch oversized for the snap rings. And then lastly, we also, for our plates, which generally can actually get pretty heavy when we're going with a lot of mechanisms on our robot, we like to pocket our plates out. We generally make our bearing and bushing holes to be 0.010 of an inch undersized, so that then we can ream them out to be a nice fit for the bearing or bushing, so they're not wiggling around at all. And this actually saves us a bunch of weight on our robot, allowing us to actually fit all of these huge mechanisms on there.
All right, Zatara, I think you're going to talk a little bit about how we track parts.
Yep, I'll be talking about that. So basically for our, keeping track of parts, we believe on 1678 that our designers, the job of the designer is not complete when the model is done. So a big philosophy is basically the designer should and will be present for the entirety of the design process, from getting the tool paths out, from getting the drawings out, to having it be made, assembled, and first tested, because the designer should be informed of any and all decisions that are made about the changes for their mechanism and the second iteration, and therefore we use a parts tracking sheet. So Mike, I think we can hop over. Basically, we actually have a naming convention for all of our parts to make sure we can actually keep track of it. So every single part, excluding COTS parts or purchased off the shelf parts, are given their own ID. This ID consists of our team number dash the year. So for example, this year would be 2020 dash part number and an assembly. And of course, the last number is its assembly number. So as you guys can see, we're actually able to generate our own parts just by typing in information such as the machinist name, what assembly it goes to, the quantity, and its status. And I'd also like to mention that on Team 1678, we actually divide our substructures, I think is what FRC calls it, into assemblies. And each of those assemblies, we give it a number. We took that straight from 254. Basically, every single assembly gets its own number. So for example, the drivetrain will be the O100 assembly. Intake will be O200, Wrangler will be O600, and so forth. And by automatically generating part numbers, the part number is inserted into the top tab, and we're able to keep track of extra stuff there.
Awesome, thanks, Zatara. All right, Zach, you want to talk about our assembly process?
Yeah, so as Zatara said before, really the designer's job doesn't really end with the actual modeling of the robot. They go into the actual assembly process as well to make it, because they're generally going to be the most aware of how everything kind of gets put together. And so it makes it a lot easier to address issues, to find what might be wrong with something and how to be able to fix this quickly. And then also if we, any cost parts that are not there on the on that iteration will be ordered on a purchase order that we make probably about once, maybe twice a week when the iteration is finalized. And then, yeah, our primary fasteners that we use are 1032 bolts, which are about 3/16. And then we have 1/4 bolts, and then 3/16 rivets. And for those bolts, we use socket head, button head, and flathead cap screws.
Okay, that's the end of our formal presentation. But Christine, I think there's been some questions coming in. So you want to let us know what we're doing for the Q&A?
Yeah, for sure. So James will be leading the Q&A along with Andrew, so I'm going to let him take it away.
Thank you so much for the awesome presentation. Next, we'll be moving into the Q&A section. If you have any questions, please make sure to drop them in the Q&A box now. Unfortunately, we have too many questions than we have time for, but we'll do our best to get everyone's everyone's questions answered. So the first question is from Chief Delphi. What is the biggest non-technical driver behind your team's success? This can be 1678 specifically or FRC generally.
I have a quick answer for that. Our success is driven by the strength of our student leadership group, not just the formal sub-team leads, but Zach, Satara, and Nathan have all held leadership roles in one capacity or another, whether that's a sub-team lead or an outreach lead. Their drivenness towards our team's goals is what makes our team the program it is today.
I think it also has to do with the way our team is structured allows for specialization. So when you join the team, you go into design, or you go into fabrication or programming, and it really allows kids to do what they're interested in and learn from the more experienced members of that sub team. And by doing that, we can kind of create a better culture around learning and building a good robot. So.
A question from chat. Do you typically build full robot prototypes, or did you just happen to start that this year?
I don't think we've ever built a full robot prototype. I mean, we do tend to model up a general full robot, at least we did this year. But our prototypes tend to generally, they just are a mechanism maybe attached to a drivetrain if it's an intake, that we always have at least like a tank drive laying around that we can throw an intake on, or maybe we just build something out of plywood. We never build like full prototype robots that are drivable and have mechanisms that move.
Yeah,
I think that was the question.
Nathan, I think he's talking about this robot I just threw back on the share just so people could look at it. Now, I want to emphasize that, this was everybody's best crack at the first rev of the robot. So I don't want to sugarcoat things. Like, the first rev of the robot was not very good. And, I think everybody on our team recognizes that, we build something and we realize a lot of ways to improve it. But the intake, for example, Zach was Mr. Intake the whole season. And this was his first stab at making the intake, right? Like, this is using routed polycarb parts with some bent sheet metal plates. And, I think Zach will, echo that it just didn't all come together great in the first rev. Like, there were some issues with the Neo 550 gearbox, right? For example. So Zach, do you want to just talk through a little bit of what was it like building this first intake versus the last intake you made, for example?
Well, I mean, it's obviously going to be a full learning process, right? Like, as you go through all of this, you learn a lot more of what will work and what won't work. So yeah, I mean, on this first one, first of all, we were going with a 4-bar, instead of what we ended up doing to make the intake kind of collapse more vertically in the end, which was involving some surgical tubing, and that ended up making it a lot more compact. We found that there were a lot of dead spots in this first rev. The balls would get hung up on the edge of the intake arms. They would kind of get caught there. It's a lot more interesting going in at the beginning, because you do have to kind of just make a few assumptions, because you can't go into everything just kind of knowing everything. But yeah.
Thanks, Zach. Yeah, hopefully that helps answer the question. This may look like a janky prototype, but a lot of this was our best shot at the time. But we learned a lot of things to this, including I think a big thing that Nathan and I learned was having a turret at the bottom when there's a massive head of 4 motors that's 15 inches up from that turret is not a good idea, because this thing shook a ton. So we added a whole upper bearing slew in the next rev of the robot to try to address that. There were a ton of things we learned from the first rev of the robot. but it wasn't necessarily designed as a prototype. It was designed to be something that maybe we could possibly field, and it did not end up like that at all.
It's easy to classify as a prototype just because of the laser cut wood, but that was, in reality, that was because our routers were broken at the time. We just had to get something out there.
So the next question is from Chief Delphi. Which robot do you most regret 1678 building? Whether it was overambitious, not ambitious enough, flawed competitive strategy, or etc. How would you change that for this season?
I think I can speak for all of us when I say 2019. Doing the triple climb, as cool as it was just not practical in the end at all. And we definitely saw that on Einstein. I think building a lot of a smaller robot and something with that could buddy climb separately would have been a lot more practical. But we made assumptions at the beginning of the season. We went with it, so there's not much you can do.
Our next question from chat. What tools or procedures do you use to build your prototypes? What data do you collect from these prototypes?
Yeah, I guess I can speak for that. So basically, I guess for building our prototypes, we want to get these things out fast. So in this previous season, or sorry, the 2020 season, we actually got a new laser cutter. And that thing is 10 billion % faster than our CNC machines. So we try to limit our designs to being able to run on those and get those out as fast as possible. As for data, I may not be able to talk about specifics just because I haven't designed anything with that specific data needed. But basically, I think one philosophy we have is to fail faster, find out what works, find out what doesn't work, and how to fix the things that don't work.
Let me just, because we're showing some insights into what we're doing. I'm just sharing my screen now. This is part of our Google Drive. We have a folder for every prototyping group, and then they're supposed to have a log of what they're doing. This one looks okay. There's a lot of pictures and video from the prototyping group's process, showing this was the Wrangler. So this was, like Zatara mentioned, laser cut Wrangler. I think, Zatara, didn't you take 1/48 CAD and pretty much just laser cut that for our first draft Wrangler?
I just got their CAD model, copy pasted, slapped it on the laser cutter, and we're actually testing in less than a week of starting build season.
So here they're learning what the good lift points are. Obviously, connecting right there was not a good lift point, but we learned that through this process. So, yeah.
So our next question is from Chief Delphi. Once build season starts, how quickly does your team start making prototypes? And what methods of prototyping does your team like to use and have found the most success with?
Yeah, so we start almost immediately. So we have the first 3 days dedicated to figuring out what our robot's going to do, and more generally, how it's going to do it. And then from there, we decide what mechanisms we need to prototype. Generally, it's about 4 or 5. And then on day 4, we start prototyping. The main materials we use for that are a lot of plywood, old robot frames, and sometimes extrusion if we need some more sturdy moving parts. But yeah, generally it's all made out of plywood, like old rollers that we have for intakes, old shooter wheels, stuff that we have laying around in our shop from past years.
And we try to kick that process off quickly by having assigned prototyping teams before the season starts. So we don't know what the groups are going to be yet. So this mechanism field is blank at the start of the season. But after kickoff and after the first couple of days, like Nathan mentioned, we just basically talk to the student leads and figure out who wants to take on what system. And then we assign them a mentor to support, and the students take over on prototyping their given subsystem.
Our next question is from chat. How do you train your designers, and when do they start learning CAD? When do they focus on manufacturing?
Yeah, so I guess I'll speak to this one because I kind of led that process this year. I guess the off season starts at the beginning of the school year, and that's when all of our new members join the team. So we start right away getting them learning Onshape, doing the Onshape courses. Once they've gone through those, we go into some more 1678 specific stuff, learning like pneumatic movement, how to more generally design and like put together assemblies, stuff like that, how to design 3D printed parts. So yeah, we really jump right into it and take full advantage of that 3 months or 4 months we have before build season to get our designers on to the point where they can help out during build season.
So our next question from Chief Delphi is, how do you make your competitive spirit and drive contagious to your students?
I don't know. Does the student want to talk about how they, I mean, I would say, you know, one huge way to do it is by modeling what it looks like to drive to succeed and to excel. So I think the students will catch on to what they see mostly in other students, to be fair, and less so in the old adults in the room. You know, like we can say all we want, but I think what I've noticed inspires students more is when they see their peers doing really amazing things and trying to do really cool things. So I don't know if any of the students maybe have like role models they've looked up to on the team that maybe inspired them to push harder and to do more. You guys have anything you want to share on that? Completely uninspired by the rest of the team.
I mean, I guess for me, it's more about the community than anything. If you have good friends on a team, then you're going to want to work harder. And for me, at least, the design lead last year, his name was Evan, made good friends with him, and in that way learned a lot from him. So I guess just by making your team a good community and a place where people feel comfortable hanging out in general, it's a good strategy.
Mm-hmm. Yeah, I can agree with Nathan. A lot of things I learned were actually from other students. We try to, you know, base our team around student learning from student to student. So just learning, teaching, getting together with our, you know, other members on the team, I get inspired by them. I get excited. So when competition rolls around, I get hyped.
A big question from chat is your design tool public?
I don't think it has been yet, but Nathan, I don't see why we wouldn't. I mean, we pretty much just copied everyone else's design tool for 85% of what's in there, right? So
yeah, it really is just copy paste.
Yeah. We can definitely share it. Yeah, expect a link on Chief Delphi at some point soon.
So this one is also from chat. What is the relationship between students and mentors like?
So, I mean, I'll take this one less. Yeah, I mean, it's definitely a working relationship. I guess in my eyes, the team is kind of treated as a startup in a sense, in that I guess you're all working and there's a mutual respect between all students and a trust between all students that everyone is working toward the same goal. So in that way, I guess the relationship is, I guess the best way to describe it is a working relationship and community, I guess. I don't really.
Yeah, I think you did a good job describing it, Nathan. I mean, we're all, like you said, we're all working towards a common set of goals. I mean, our motto is educate, empower, excel. And, you know, as a mentor on the team, you know, I'm seeking to do all three of those things, you know, with the students. So, you know, I want them to be, you know, well, you know, educated and developed in the whatever area of the team they're in, right? I want them to be empowered, and I want to see other students in the community be empowered. And then I want them to excel. Like I want to see them aim high and try to reach new heights with this team. And I think, you know, we see students year over year doing that, and it's our job as mentors to play a part in that and to facilitate that. And I think, you know, part of that looks like, I mean, for me, you know, they're doing all the design, not necessarily because I wouldn't love to like do design. It's because, I want to see them grow, and also like I don't really have the time to do it myself. So the best way for us to excel is to see these design kids like see what they got and have them flex their muscles, and they do a great job year over year. And a part of that is due to the ways that I, as a mentor, am pushing them to excel. But I think a bigger part of that is due to the education that they have. Hopefully, like people in this call got to hear a lot from them and learn what they do to design great robots. They do a lot, and they've learned a lot over the years they've been on the team, and it's a part of our method of excelling. So as a mentor, I can help facilitate that, but it's really, that's what I'm here to do. I'm here to help facilitate all of our team goals.
Another question from chat. Has 1678 ever experimented with bent sheet metal construction like 148 or 111?
Yeah, so I guess on our team, we do have bent sheet metal parts, though we try to avoid it just because having to bend a part adds an extra step in the manufacturing process. So for example, a designer could make a part, then they have to either get a toolpath or drawing out, they have to get it manufactured, and adding the extra step to, say, bend it, we might not have enough time, so we try to cut that out of the picture when possible, try to keep it simple, so we just try to avoid sheet metal parts. Though we do use them, I wouldn't say we haven't experimented with them, but it's definitely there.
Yeah, we don't. Yeah, go Nathan.
Okay, yeah. I mean, you'll see them on a robot, but we generally try to stay away with them. Keep the design more simple. We have tube for a reason. We don't need to make sheet metal tube. And I guess the main bent part on our robot this year was the tower in the middle. The rotating tower was two like bent pieces of sheet metal that made a 12-sided shape going up the middle of a robot that held our sheeter. That was a pretty cool part. But
so the next question from chat is, how do you make sure your electronics are accessible during competition?
They're not. Is that a good answer? Yeah, they're mostly a pain to work with every year.
Yeah, in retrospect, we definitely should have done a flipped belly pan this year, but you can't have everything.
Another question from chat. With the gear ratio between the mechanism output and encoder, how are you handling zeroing the encoder? And are you worried about loss of position during brownout?
So for zeroing, we use Hall effects, not the encoder. I guess the Falcons have proved to be a little bit iffy when it comes to encoder ticks, especially on our climber this year. So we use a Hall effect sensor for each, or I guess we did for the Wheel of Doom, except we didn't end up actually needing it because we weren't zeroing that. But for the turret, we have a Hall effect that triggers once every rotation. And then also for something like an elevator, we would put a Hall effect at the bottom of the elevator just to zero it every time it goes down and reset the encoder.
So from chat, we have a question. Can you explain the configuration of the wheels of the 2020 drivetrain?
Yeah, I can handle that. So basically, we have an 8-wheel West Coast drive with 4 6-inch pneumatic wheels located at each corner of the drivetrain, and then 4 6-inch Colsons at the center, and those are dropped, I believe, 1/16 of an inch.
The main ideology was just kind of copying our 2016 drivetrain bar the middle wheel, just because of the way it kind of skipped over the bar when we took some slow-mo video of it like day 3. So really not much thought process except some testing.
How do y'all recruit new members?
One of the students want to go through our recruitment process?
I can take it if no one else will. So generally, we try to reach out to our schools. We live in a pretty small town with about, we have 3 junior high schools and 1 main high school. So what we do is we actually, our junior highs go through 9th grade. So we take those 9th graders who are still at the junior highs and they give presentations at math classes throughout each school, and we get the word out that way. And then we also have a recruitment day near the end of the school year that we invite students to come to and figure out what they might be interested in our team and hopefully join.
So from chat, there's a question on how you market your team to your community.
Okay, well, we do a lot of community outreach. Generally, like I said, we have the 3 junior highs, but we also have classes at each of those schools. And we also have elementary school programs running at, I think, all 8 elementary schools except 1, I think. So we kind of have put ourselves out there to the younger kids. So kind of coming into high school, many kids might know the name of our team or know who we are. And then we also have social media, and we usually have UC Davis as a sponsor. So in that way, we're kind of out there to in our community, spreading the word about our team.
Another question from chat. What would you improve on this year's robot?
Zatara, what would you improve?
I think that climbing arms that flip up were just not the move. I think something like a 3-stage telescoping elevator like 4414 would just been much more better, a lot more compact, because those arms were hanging over the robots. And then I'd also think that the buddy climb in the end was not necessary. It took up a lot of room in the back of the robot. So if it just wasn't there in the first place, we could have had a lot of room for the Wheel of Doom or maybe even the shooter.
So our next question is also from chat. How do y'all stay on schedule?
Yeah, so before build season, I was in charge of kind of putting together our build season schedule, which we print out on a huge piece of paper and paste on the wall first week of build season. And we try to set an extremely accelerated schedule. So what that looks like is prototyping as quickly as possible and trying to have a full robot by the end of week 5, like the very latest. A lot of times we don't hit that exactly, at least we didn't this year, just because this robot was much more integrated than, or the mechanisms were much more integrated together than in the past years. But generally, we just try to hold a super accelerated schedule, hold extra meetings whenever we can. And that way, I mean, it really comes from the students wanting to get this project done more than anything. It's not like the mentors are scheduling extra meetings. The students are taking initiative, scheduling meetings for assembly time and shop time. So yeah.
From chat, do you have a compressor on the robot, and how are you calculating air volume?
Yeah, so Mike, can you bring up the design sheet? So I do believe it is in the rules that if you are using pneumatics on your robot this year, you're required to have a compressor on your robots. And then for calculating how much air we actually need, we enter in the details of the cylinder. So for example, the bore, the length, and the quantity. And we actually also, guess how much actuations you'll make per match. And with how much pressure we're putting into each of those cylinders, we can calculate how much volume per cylinder we'll be using. We add that up to get our total volume of air used per match, what percentage of the total air volume is used, and then our tool calculates how much air tanks we need.
Yeah, and this is done, like the key for this tool, this is, I think, a tool 1114 published a long time ago that we just put into Google Sheets. But the key with it is figuring out, obviously, like the length, all the specs, but what you have to estimate is how many actuations you expect that mechanism to use per match. That's kind of the golden ticket. It's hard to get that right because, maybe your operator accidentally double presses the intake button and has to reactuate it a couple times in a match. You just want to be a little bit conservative, but there's other things where you can clearly say, okay, for example, the Wrangler deploy, we're only ever going to deploy the Wrangler at most once a match, at the very end of the match. So that's an easy one to be able to say how much air that system is going to use.
So this question is from Chief Delphi. How is your team staying engaged during the COVID-19 shutdown?
Yeah, so I guess I can speak for design. I'm not really tuned into many of the other sub teams right now, but design has been doing remote meetings every week, working on off-season robots and improvement to our current robot. And we just kind of assign work remotely, delegate it out, and then kind of meet back every week and have a design review, and then just repeat that.
Another question from Chief Delphi. How was no bag for 1678?
I'd say overall it went okay. You know, we, like the team, 1678 has been an advocate for not having the bag, but to be honest, like the bag was an advantage competitively for our team because we build 3 robots. So we had 2 other robots to use while most other teams had their robot locked up in a bag. You know, I think maybe some of the other designers can key in, but I think the one trap with no bag is you end up working on your robot way later into the season than you expect to. And so it can be harder to prioritize driver practice because you can always be improving some mechanism on the robot. I don't know if Nathan or others have thoughts on that, but that was one of my big takeaways.
Yeah, definitely. And especially like people assumed we would be on top of things because we put out that teaser really early. But to be completely honest with you, when we put out that teaser, our competition robot was just a drivetrain still. We did not have anything on that robot. And I only ended up getting maybe a full day or 2 of driver practice before LA North. And honestly, that probably affected our gameplay. And so yeah, like Mike said, it definitely is a trap. And yeah, I definitely tell you, we were making improvements to the last minute. So
this is another one from Chief Delphi. How's your position on Swerve changed over the years? If yes, how so?
I mean, just on a high level, the ability to buy solutions and then the ability to use motors with integrated encoders has definitely changed our calculus on Swerve as a whole. I wouldn't say we're committed, you know, to one over the other, but it's become pretty clear in the last couple of years that there's been some real success stories with the Swerve drive. Obviously, our friends on Madtown proved everybody, you know, that Swerve is a good option after they danced around the competition in 2019. In 2010 is in a similar boat, having proved that Swerve drive can be really advantageous. So I will say it's something we are looking into. It's not something we've committed to, but it is a nice thing to have, especially because you can just buy it. And, you know, I think the kids will echo this, but we would never build our own. We would never like manufacture every part of it. We're just going to buy whatever the best one is if we end up using it. So, yeah.
So this one is also from chat. What is the size of the 1678 design team?
So I think we're at about 15 kids right now. Yeah.
What CNC router do you have or use?
Yeah, so we have 4 CNC routers. We have 1 V-Lock router, and we have it's a big 4 feet by 8 feet router, and then we also have 3 Omeo routers, 2 of which are Chinese knockoffs. They're really small. I believe it's about 2 foot by 3.5 foot, and we use those for manufacturing smaller gussets while we use the big V-Lock for just, you know, making big stuff.
Will 1678 release your robot CAD this year?
Yeah,
Yep.
We definitely will at some point. We just don't have a date yet for that. We might be waiting a little bit.
What teams will you look up to?
I'd say for me, I think Madtown definitely. Their robots are always super clean. You know, they're always really competitive. But I can't get enough of watching the robot in 2019. I'm going to be honest. They are really pretty out there.
Yeah, and I'll say, you know, another team, California Friends, or 254, we we probably wouldn't be overall, like over the last 10 years since we've been trying to be more competitive. I don't think we'd be where we're at without 254's influence from before we won our first regional in 2011, we went to 254's shop to practice on their practice field. And that was a really formative experience for even that small group of students that we had on the team back then. And I think it's just accelerated since then. And so 254 has really set the bar for our whole region and probably the whole community.
Cool, thank you so much. I think we're just about out of time. Thank you everyone for coming to our show, to First in Focus, and thank you Citrus for your great presentation.